while you are doing that, I will introduce this team. So this team is working on a project titled the Design, Fabrication, and Testing of an Improved Feedstock Powder Spreading System. This is a collaboration with Dr. Molin's group at the National Institute of Standards and Technology. And as you know, UDC is part of the team funded by National Institute of Standards and Technology. So this project is to work on a redesign of this feedstock powder spreading system. Has been developed in his team, in his group, and the student here is trying to provide improved design for this system and allow the flexibility of adding different camera system to monitor the process of the powder spreading during the additive manufacturing process. So Dr. Molin has joined us yet.
I'm here.
Oh, you're here? Okay.
Yep.
Thank you for
good
joining.
Morning.
Yeah, good morning. So with that, I will turn over to the team. And also, I think there was a comment earlier for when you present, yeah, I think don't use the presenter view so the people can see the whole slides. Right. So I'll let this group start. So you can start it whenever you're ready.
All right. Thanks. Good morning, everyone. I hope everyone is doing well despite this current situation. I also trust that everyone is equally as excited to hear our presentation as we are to present. So just to jump right in, my name is Javel Wilson. I'm accompanied virtually, of course, by Mohammad Alghamdi and Juvani Downer. As Dr. Shu mentioned, this is a joint effort with the National Institute of Standards and Technology, with our main liaison being Dr. Shawn Moylan. So just to give you an idea of how we're going to present this information to you, so we'll go through our introduction and motivation towards this project, then transition into our overall project description, point out some of the findings that we stumbled upon, and take you through our strategic brainstorming process. So kind of the thought process before jumping into generating our design concepts. We'll then importantly point out our actuator selection, circuit design and installation, of how some of our electrical engineering skill sets came into play. Show you a basic model that we managed to create in interactive physics, make some final conclusions, future works, and so in whatever context additive manufacturing is heard, essentially refers to 3D printing, and everyone is quite familiar of the advantages that additive manufacturing allow. However, for the scope of this project, we'll be focusing on the powder bed fusion process, which is a subset of the AM process, whereby a heat source in the form of a laser, electron beam, or thermal printhead is used to melt and fuse material in the feedstock powder form, as you can see from that image over there on the right. So one practical advantage of the PBF process is that it's one of very few AM techniques capable of producing fully dense parts with properties approaching raw material. And this PBF process can be divided into two sub-processes, namely the powder spreading, which is usually done by a blade or roller mechanism, and also the sintering, which is the melting and fusing of the powder essentially. So this is just an image showing you what kind of the computer interface of most of these PBF systems look like. So you have some luxury of controlling certain laser parameters, or controlling the sintering process by controlling the hat spacing, laser power, and things of that nature. So this is basically showing those parts on the build plate, and this is kind of what the virtual or the computer system looks like for most of the printers. So here you have an initial dose of powder distributed, and then you have that recoating arm or roller mechanism coming across, taking that powder across the surface, and then going back across to remove any excess powder that may not have been properly spread. Then a laser comes in and sinters that material. This is just like an actual image of the internal chamber of the system. So after the material is sintered and after the final print is made, after doing that process continuously, the build plate is then retracted, and then the excess powder can be removed with a vacuum pump, and then those parts can be wire EDM'd off or some other form of removal. So if you move on, so I want to, spend some time on this and making this clear as to why our effort is essentially important. So as I mentioned before, the powder bed fusion is divided into two main processes: the powder spreading and the sintering of that metal powder. So research has shown that there are certain parameters that I've mentioned that you can control from the printer involved in the sintering process, such as the laser power, the dwell time, the hatch spacing, all significantly contribute to the quality of the final part in ways such as surface roughness and porosity. However, the uniformity of the spread layers also significantly contribute to the final part, but there has been limited research done to really make a solid relationship between what exact mechanisms of the spreading process contributes to the quality of the final part. And this is how our effort really becomes valuable.
So NIST made an initial effort back in 2018 to actually create a powder bed fusion system. However, this system had a few primary limitations, those including the inability to disperse a repeatable amount of feedstock powder onto that silver platform that you see in the image on the left, meaning that they had to manually distribute a dose of powder onto the platform so the gram amount would not be consistent. The system was also confined, meaning that it was pretty small. And if they wanted to test larger samples, say 10 grams or 15 grams of powder, they would not have the capability to do so. Another thing that we discovered was that the camera setup that they have was affixed, meaning that they could not capture the entire spreading process. Now, if you take a look at the image on the right, you can see some powder particles there, or powder particle profile, but if you put an initial dose of powder onto the platform, you would not be able to see that from the camera. Also, you would not be able to see what the powder profile looks like after the spreading process has been completed due to the fact that it was not in the view of the camera.
Yeah, so kind of some of the research that we stumbled on, and this one became valuable to us for some extent. So the process is called the particle surface tribology analysis, PSTAC code. So essentially what they do is they characterize AM powder using a powder rheometer, which gives them an understanding of the flowability versus forces. And then this rheometer data is essentially used to calibrate virtual powder, and then they can execute virtual spreads through a software. So with this data, they can then pair this information with regression algorithms based on machine learning codes to create kind of these spreading process maps, so they can get an understanding of what the velocity magnitude is at different points of the spread. However, there is some calculations that would be involved in this simulation, namely the particle-to-particle collision and also the particle-to-substrate collision. However, that would kind of be outside of our capability here in house. But what really struck out to us was the rheometer aspect, because we did have some data that we could leverage from NIST, from a powder rheometer that they have that they were using to characterize some of those samples that they used for their initial prototype. So this would kind of give us an idea of what the general flowability of the powder spreads would be subjected to certain forces, which was forces that we could calculate. So we thought that this was valuable in that regard.
So moving to the project description, I just want to first point out that it's very difficult to study the characteristic and spreadability of powder involved in commercial powder pit fusion systems without affecting the environmental condition and operation of the actual system. And so our project description is to design, fabricate, and test feedstock powder spreading system with the flexibility and robustness to facilitate detailed analysis, provide a holistic insight into powder spreading process, which a commercial powder pit fusion system would not allow for. However, to ensure that the new design will have the capabilities and luxury to do that, we'd have to possibly incorporate some of the following design requirements. So first design requirement to the top is to allow our system to fit in for in-situ imaging and monitoring of the spreading process. There will be 2 cameras to inspect the area behind the recoating arm and the whole powder layer while it's being spread across the substrate. Moving to the next design requirement, which is to ensure that the recoating arm will have the ability to distribute an evenly powder layer across a wide range of surface. So the size of the recoating arm has to be bigger relative to the prototype we've seen at NIST. Moving to the next requirement, which is to design a recoating mechanism that can capture excess powder after each layer is completed. So in the previous video, which my teammate Javel just went through, we've seen that after each layer is completed, there will be a leftover powder. And so our goal is to capture that excess powder. And the next requirement is to give the system the ability to test multiple substrate surfaces. So the substrate or the building platform should be removable. The last but not least requirement is to make sure that the design can provide accurate metal powder goes to the recoating arm, or in other words, meaning that the amount of powder coming from the powder chamber should always be the same each time a layer is complete.
So after we kind of identified what those design requirements would be, we kind of went into some amount of brainstorming before we, kind of to have some more information before we started to jump in and generate our design concepts. So we created a SWOT analysis. We kind of identified the strengths, weaknesses, opportunities, and threats of our design. So strengths, human resources, we did have the capability to leverage Dr. Moylan and also faculty here in-house if we, stumble upon any roadblocks. We had a budget of $10,000 for this project, so we had no intentions of designing a system that would be that costly. So we did have that as a strength also, and some amount of prior exposure. Myself and Juvani has been exposed to this AM process before through internships, so we weren't going in super blindly into this project. Weaknesses, we did have some amount of limited machine expertise. And even though our machine shop was capable, it was still pretty restrictive in some regards. So opportunities, as I said, this is a very important aspect of the AM processes because there isn't a lot of research that connects the mechanisms of the spreading process to the effects of the final print. So it could be good in that regard, and also kind of tying into the work that NIST does. This could possibly establish AM powder bed fusion standards. So threats, injuries, and also inability to access lab facilities, which was something that actually came into play with the whole COVID situation, which kind of inhibited our fabrication process. So kind of we generated also a morphological chart. I won't spend too much time on this because we'll actually go into these solutions, but we basically, generated some amount of solutions that we could use to achieve certain functionalities, and then we selected the best selection based on certain criteria, but we'll go more into that. So if you move on.
So we did go ahead and develop a quality functional deployment chart to establish some level of priority between, say, the customer requirements and the main components that we would need to achieve the primary function of our system. We did have some customer constraints in the form of the system had to be laboratory desktop compatible, and we did have a budget of, say, $10,000. Now, 2 customer requirements that we did look at was the repeatable powder dispersion as well as uniform powder spreading. As you can see, we gave them a rating of 5, 5 being the highest level of priority, and the functionalities that we used to actually meet these 2 requirements was having a power supply, as well as an Arduino microcontroller and linear actuators. These are represented by a strong relationship with that blue circular icon that is distributed across the chart. Now, moving through the design development, the first design concept that's on our left saw us designing a powder dispersion plate that allows for repeatable powder dosages. And this powder dispersion plate is connected to a linear actuator that allows some translation in the Z plane. We also had an additional setup for a camera to kind of track the overall process of the powder spreading system. We also had an extra ball screw linear actuator that would have allowed for some camera mount so that we can see what's happening while the recoating arm is moving across the build plate platform. Now, as time went by, we came up with a new design concept, and those can be highlighted with the components that are in a different color, such as we specified the ball screw linear actuator that we were going to use for the system, as well as we decided to mount our system on an air table for a high level of stability. Now, to finalize our design concept, we did go ahead and remove the extra ball screw linear actuator for the camera, as we did not know how this component could affect the optic of the system. However, we did choose a specific motor for the system, as well as we did implement a wheel that would be attached to the recoating arm to kind of prevent a cantilever beam effect occurring to our system, as well as providing some level of stability for the recoating arm that would translate across the build platform.
So moving to the control system aspect of our project, first we had to go through the selection of linear actuators. To select the linear actuators, we did some basic calculation to estimate the weight of the parts. The actuator was a part to ensure that the actuators will not exceed its maximum load capacity, and also make sure that they have the required stroke length. So using aluminum 6061, which has a density of 2,700 kilogram per cubic meter, we estimated the weight of the build plate, recoating arm, substrate, and dispersion plate, as you can see. And with the load capacity of 250 pounds, I'd say we are safe and weight shouldn't be an issue whatsoever. As for the displacement in extension and compression, the selected linear actuator has a stroke length of 4 inches, which is appropriate and sufficient for our design. Moving to the next slide, here to control this actuator, we use Arduino Uno as a microcontroller and 2 double channel relay modules as shown in the schematic diagram. The Arduino Uno was chosen because of its simplicity and also because we've had some background experience working with it from previous classes and projects. We also use the relay module to switch the polarity of linear actuator, which will help control the extension and retraction. And also it will help the Arduino interfere with a higher voltage devices, such as the 12 voltage linear actuator. So in the next slide here, we video shows a first attempt when we first were able to control one of the linear actuator. As you can see in the video, we implemented 2 buttons to control the extension and compression of the linear actuator. And in the next video is pretty much the same, except that we're now controlling both linear actuator at the same time with 4 buttons, 2 buttons for each linear actuator. Now, excuse us for the poor quality, but the video was not meant to be for a PowerPoint purposes. So moving to the displacement calculation, now we developed a code in Arduino software to control the extension and compression by setting a time delay. So to calculate the displacement caused by a specified time delay, we have to know the stroke length, which is 4 inches, as I mentioned before, and the time the actuator take to go from full compression to full extension, which is 6.5 seconds. So doing simple calculation, we can define the displacement caused by using a specified time delay. If we take a look at the lower part, we have an example of how to calculate the amount of powder needed to create a layer with a certain thickness. So by multiplying the height of powder by the width and length of the area in which the powder will be distributed on, we can get the volume of the powder required. Now, by dividing the, if you take a look also at the bottom calculation, by dividing that volume over the length of the dispersion plate multiplied by the width of the dispersion plate, we can get the required extension height to get that volume. Now, the next type of actuator is the ball screw linear actuator, and it consists of the ball screw assembly and the stepper motor, as you can see in the right loop. Also, we are using Arduino Uno and micro stepping short driver to control the stepper motor. So the short driver allows us to convert the command pulses coming from the Arduino Uno into an actual motor driving steps. And it also helps control the position, speed, and acceleration of the stepper motor. So as for the code, we developed a code that let the user control the position, speed, and acceleration of the stepper motor through a command window that can be displayed on laptop. And these parameters will be defined in terms of steps. So to control the linear distance of the recoating arm, we did basic calculation to convert the steps to inches. So if we take a look at the calculation at the left side, the motor requires 2,000 steps to make one revolution. And one revolution is equivalent to 0.5 inches linear motion. Now that's because the ball screw has a lead of 0.5 inches. Knowing the relationship between rotational motion and linear motion, we can also define how many steps we need to drive the ball screw assembly for a certain displacement. And same thing can also be applied to calculate the velocity. Now, in the next slide here, also another schematic for the circuit diagram. This schematic is actually very simple. As you can see, everything is connected to the show driver, the power supply, the stepper motor, and the Arduino as well. All of them are connected to the show driver. Now, the next slide, if we take a look at the left video is showing the stepper motor rotating clockwise at low speed and low acceleration and deceleration. And the right video is showing the stepper motor rotating counterclockwise at higher speed and higher acceleration and deceleration.
Yeah, so kind of touching on this, we thought that this was important to show because one of the things that we want to consider is, so for typical PBF machines, the speed of the spreader speed is something that affects the quality of the spread. And for most systems, it pretty much has a large range of, I think, 40 millimeters per second to 500 millimeters per second. So for our miniaturized version, we kind of selected the lower threshold of 40 to 100, but we needed to understand what our motor inputs had to be in order to achieve that velocity of the recoating arm. So we also looked at making a correlation between those RPM values and also what our torque inputs for a motor would be based on this graph that was provided actually by the manufacturers of the stepper motor. So if you go to the next slide.
Yeah, so here we have our interactive physics model simulation. However, before we got the simulation up and running, we had to define some inputs, such as the mass of the recoating arm, the speed of the motor shaft diameter, some build dimensions, as well as some static and kinetic friction factors. Now, the purpose of this simulation is to validate the speed of the recoating arm that we gathered from the table before this slide. And here we have the simulation running, moving the recoating arm across the build plate platform. So one thing about interactive physics, you can always display different output values. For this instance, we paused the simulation midway and gathered the velocity values from the simulation and chart as well. Now, once we did this, we were able to test each RPM that the motor generated from our chart and match it to the interactive physics speed of the recoating arm. As we can see, the interactive physics speed of the recoating arm varies from the actual calculated value that we got by some 20 to 30 plus millimeters per second. And this is probably because of interactive physics limitation, meaning that you cannot input more than one parameters at a time. And a perfect example would be we could only input the RPM value of the motor. We could not manipulate the torque while running the simulation, and vice versa is true. So we are assuming that this might be some of the shortcomings as to why there's an inconsistent reading in the actual values for our interactive physics speed versus the actual speed of the recoating arm.
Yeah, just before I conclude, I want to make just the simulations clear. I don't think it was really properly introduced, but so basically all of our calculations prior are even though we're confident in these calculations, they're solely theoretical. So we needed to fabricate an actual system in order to validate these calculations, but owing to the current situation, we did not get a chance to do so. So the idea was to emphasize more of the simulation, and what we wanted to do was we had an understanding, or we made some calculations as to what speeds we expected from the recoating arm, just from a hand calculation perspective regarding certain inputs that we made for the motors. So the purpose of the simulation was to validate those hand calculations to see if when we simulate the system with those conditions, we were also able to make some kinetic and static friction coefficient considerations in the simulation. So we wanted to validate those speeds that we expected for the recoating arm. But as Juvani said, we had some slight inconsistencies. The values were off by about 20 to 30 millimeters per second. And that could be as a result of the system, the simulation being limited in that we can't look at the impact of two parameters at the same time. So when you think of a motor, both speed and torque is playing a role in the translation of the arm, but in the software, we're only able to evaluate one of those parameters. So I just wanted to clear that up, but some of the conclusions, so we have successfully modeled all components of the feedstock powder spread system in Creo. We successfully programmed for the linear and ball screw linear actuators using Arduino microcontrollers and the Shore drive. And we developed a simple interactive physics model to aim to simulate the motion of the system and validate the expected recoating arm. We definitely have some work to do there. But for future works, again, fabrication of an actual prototype in an effort to validate the efficiency of our design is really mandatory. And that's something that we regret not having the opportunity to do, but the situation is out of our control. Performing vibration analysis on the recoating arm. So we have a motor and we expect some level of vibration to be coming from that motor. And because it's connected to the recoating arm, the case might be that these vibrations might propagate to the spread layer. And dealing with, a certain 80 to 50 micron diameter powder, that's pretty small. So any amount of vibration might cause considerable effects. So we definitely need to, analyze the vibrations coming from that motor, possibly using an accelerometer to see if those vibrations are worth considering, and also to conduct some amount of process measurements on the spread layer. So after our system makes those spreads, we want to evaluate the uniformity of the powder dispersion to see, if we're having lumps or inconsistencies or voids anywhere in the spread, which would be things that we would need to test. So if you move on. Next slide. So yeah, acknowledgement. I just want to thank Dr. Jiajun, who was our project advisor, for his help. He really provided himself as a resource throughout this project. Shawn Moylan, I really have to thank him. He was directly available through email to answer any technical questions that we had, and he actually took the opportunity to, come and sit into all of our presentations that took place on campus and give us live feedback. So I really appreciated that, and I'm sure the team feels the same way. Dr. Max Dennis, who gave us some assistance in pointing us in the right direction at the beginning of the project. He also, provided himself as a resource to, possibly use him to conduct some of those vibrational analysis, which was something he was familiar with. And Kyrie Beckett, senior, obviously we didn't do all that electrical engineering work by herself. I'm really proud of the electrical engineering efforts that we managed to achieve nonetheless, but I want to take the time to thank him also. These are just some of our primary references. If you skip to the next slide, but that's pretty much the end, and we'll facilitate any questions.
Right, excellent job. So before we open for your questions, I want to just remind everybody again, please fill out the survey for this team through the link in the chat box. And so now we have a couple minutes for the questions and answers. So you can either type in the chat box, or you can just unmute yourself and ask the team directly. So any questions from the audience?
Yeah, this is Shawn. If you don't mind, I have a comment and a question. If you guys can go back to the slide with future work on it, please. All right. So I guess my first point of clarification here deals with the last bullet you have there, which is to conduct post-process measurements on the spread layer. That's absolutely the analysis that we want to be able to do it with the test bed. And the only the reason I bring it up is to say a lot of the variables at play here might affect the uniformity of the powder spread. So, for example, what powder we used, sort of what's the humidity level, etc. And so, a non-uniform powder spread would by no means be a direct indication of a poor design by you guys. It might just be some of the other parameters that we put into the test. So with that in mind, I guess the question I have is about that first bullet, which is um, your efforts to validate the efficiency of your design. So did you guys think at all, and could you elaborate more on what specific testing you might have done? What sort of data would you want to collect, and what would you compare that to so that you would know whether or not your design was sufficient?
Yeah, I can take that one, and the team can support me if needs be. But so we made, as you've seen in the presentation, we made some considerations as it relates to the height elevation that we would need from the recoating arm, from the ball screw, from the linear actuators to achieve a certain height of powder layer. But as I said, those numbers are pretty theoretical. So we would actually need to, program the actuators to raise those distances to see if, we're achieving a consistent height of powder each time. Also, for the ball screw linear actuator, even though we're pretty sure it works well from just, without being connected to the actual setup, we would have to, again, evaluate the translation of the recoating arm to see if it's making good contact with whatever powder sample that it's coming in contact with, and to just see how it's spreading. I think all of our design or evaluation was theoretical, and in no way can we rely on just our theoretical perspective to see if what we designed, what we programmed was efficient. So I think we were mainly just trying to focus on that, highlighting the fact that we really need a prototype to make any kind of confident deduction. I don't know if, hello?
Yeah, I think Dr. Moylan was hoping that you can, talk more about your actual plan. If you can test it or what you plan to do, to further test it. Is that in your report?
Yeah, we elaborate more about like our future tests in our report, but yeah, I think the main thing is, even we just needed to actually have a workable prototype to figure out a direction forward. I mean, some of the things we know that one of the important things is achieving a consistent gram amount or volume amount of powder as we distribute each time. We have no idea to validate whether or not the actuators would actually achieve those, even though we have managed to program them to move at a specific displacement using a time delay. So I think there's a lot of areas that we could like expand on, but as again, it's kind of hard to predict that direction without a functional prototype.
Okay. I also want to thank Dr. Moylan for your continuous support. As the student mentioned, you have joined us the presentation from last year to today in person a couple times and provide feedback and talk to the student over and over. So thank you very much for your support. And also I want to mention that he is also our mechanical engineering advisory board member and has been supporting our program for some time. And thank you for your effort. So I saw there are a couple questions from the chat box. So the first one from Dr. Klein is asking whether you can elaborate a little more over your decision on the blade or spreader type.
Yeah, we did make some consideration, and we did find different spreader types. However, kind of a spreader, of a rectangular cross section, if I will, is the most used and kind of fully understood. Even our EOS synth metal printer downstairs pretty much uses the same type of spreader. So we didn't want to deviate much from that to cause any confusion. So we just kind of stuck to it. I mean, probably Juvani can talk more. I know we're looking into kind of optimizing or seeing which spreader type might be beneficial as it relates to kind of the contact to that powder spread layer. But as the rectangular cross section was pretty well understood, so we just thought there would be no need to deviate from it. I don't know if Giovanni has any comment.
Yeah, we were looking into optimized blade spreader types. However, that research is still ongoing. So for now, we just went ahead and stuck with the norm, which is the rectangular blade type spreader.
It's pretty well understood, and we didn't find any like problems as far as research goes as to why people would not use it. So we just kind of stayed on the safe side, to be honest.
Okay. There's another question from Dr. Chen. Is asking about the control itself. Is this a general position control or current or torque control?
I'm not so clear on the question, but and again, Mohammad can touch more on this, but for our linear actuators, we basically specify displacement based on a time delay in the Arduino code. So if we know the maximum stroke length of the actuator, we also know the total time that it takes to reach its full extension. So programming a time delay, which is associated with a button press, we're able to make the linear actuators extend a specific displacement, which we would then correlate to a specific height of powder layer that we would want to achieve. As it relates to the ball screw linear actuator, we program that again using Arduino, but it's linked to a short drive. So based on the RPM that we specify in the Arduino program for that motor, we then can do the calculation, which we've shown, of the linear translation that contributes to the recoating arm. So based on an RPM value, we would be able to predict what that linear motion would be from the recoating arm. But yeah, it's we pre-program the Arduino, and then once we run the program, it does it by itself. So I don't know if that answers that question.
So Mohammad, do you have any comment on this?
I think Javel answered that clearly. But there's a question that we missed at the top, which says if short driver has already applied any PID control for vibration. So the short driver we have comes actually with a switches, and you have to adjust these switches based on the type of motor that you have. So in our case, we have the 23 NEMA, which has a step angle of 1.8. And so the short driver comes with a specification sheet, and you have to figure out what type of switches you need to turn on and off to make the short driver compatible with your motor. And when you find the correct switch, when you turn on the correct switches, you will eliminate a lot of vibration by doing that. I hope that answers your question.
Yeah, I think the follow-up one on that from Dr. Khan is just regarding the current control system. So do they need height adjustment or calibration in your case?
Yeah, I think she's asking about the wheel support. Yeah, so the idea behind the wheel support, so we were kind of fearful of a cantilever beam effect of the recoating arm if it was just supported by a bracket at one end and then didn't have any support at the other end. So we came up with the wheel design because one, it would allow for support, but we think that it would also aid in the translation of the recoating arm. But there was some amount of uncertainty around that, and we went kind of back and forth with Shawn Moylan on this, where there might be an alignment concern of that wheel, where the motor might be kind of sending pulses to the recoating arm to move in a linear direction, but then we kind of have this rotary motion on the other end that could kind of cause some disalignment and probably affect the spread layer. So that was something that we had in the back of our minds. But again, I think we were aiming to fabricate the system and really see how well it performs. And based on that, we could make adjustments, whether it be with alignment or motor control. But I think from just a design perspective, we thought that it was feasible, but bearing in mind that there might be some alignment concerns that we had to adjust. But again, without a prototype, we have no idea of really assessing that performance. And, yeah. So that was a bit of a bottleneck. Yeah, that was kind of the idea behind it.
Okay.
Just to go back for a second on the PID, Dr. Chan's question. So it was going to be so my idea for Javel's group was going to be a position, using a position control. But first I wanted them to set it up. And then the idea would have been to use, if it was possible, to use Simulink and interface it with the Arduino board, because that's something that they're familiar with from their class. So the idea was to use a software-based PID controller using MATLAB Simulink.
Okay.
Sorry, I may have missed that. Was that a question or a comment?
I was just addressing Dr. Chan's question.
Oh, okay. Thank you for that. I thought that was a question.
All right. Thank you for your comments. Again, just to remind everybody, please fill out the survey for this team. And due to time, we're going to move on to the next group.